Hello, and welcome to Empowered Learning. This particular video will be about radical expressions as well as expressions with rational exponents. And so we're going to do things such as reduce these expressions to its most simplest form, or to its most simple form, I should say, or to lowest terms. And we're also going to multiply these expressions together, add them, subtract them. Okay. And we want to start off by just reviewing some of the vocabulary before we get into those examples. So the first thing that we want to say here is that roots are used to reverse powers, okay? And so to give you an example of what I mean by that, let's say we have 2 raised to the power of 3. We know that that is going to be equal to 8, okay? So this is what we call a power. Whenever we reverse that, what we're saying is, what number do we have to multiply times itself 3 times to get 8 here? And how we would say that is this way. In other words, what is the cube root of 8? And we know that that is 2. So here we say 2 raised to the third is equal to 8. To reverse that, we say cube root of 8 is equal to 2. Okay, and so here, when we have a root is expressed in 2 ways, one of the ways is with a radical sign, and the radical sign is what you see here, where the expression under the radical sign is called the radicand, and the number that is on this little part here is called the index. Okay, and so if you notice, the index for the example I just did was 3. Okay, so that tells us how many times we have to multiply this number times itself in order to get that one. So that's what the index means. So a root is expressed in 2 ways. One way is the radical sign, like how we see here. The second way is as a power raised to a fractional exponent. Okay. And so here, technically speaking, we could look at 2 to the third as 2 to the 3 divided by 1, okay? We normally don't do that, but technically we can look at it that way. So here, what we actually use this more so for is to take this and rewrite it like that. And of course, that just means 8 raised to the 1/3 power, and that will in turn be interpreted that way. Okay, so that's part of what we're going to be looking at here in this particular video. All right, so let's move on. So we know that roots, or nth roots rather, as we're going to call them in general, can be expressed either as an expression with the radical sign with some index, or as an expression with a fractional exponent. Okay, so we know that the symbol nth root of a is read as this, and so now for our definitions, this particular definition, if we have some expression equaling b raised to the power of n, then we know that b is what is called the nth root of a. Okay, so I was trying to explain that earlier here in the video. Okay, so all the stuff I have down here, for example, if a is equal to b squared, then we know that b is the square root of a. And so here, this is basically what we're saying. And of course here, there's an understood 2 that's right there. So we're saying that b is the square root of a, or b is root 2 of a. And we normally don't write this. We normally keep it blank. So you kind of know it as just square root of a as you see it here. But at the end of the day, we're just trying to basically figure out how we're going to notate reversing these powers, okay? And that's the main thing. So all this information that you see here basically says that. So some other basic facts about the nth root of a: if n is a positive even integer, such as 2, 4, 6, 8, 10, so on and so forth, then we take the nth root of a as being the principal root. And the principal root just means we are talking about the one that is always non-negative, okay? And so I'll get into a deeper explanation of what that means a little bit later. Next thing, if n is positive and odd, then we say that the nth root of a is just this, okay? So in other words, if we have a situation like that, then we know we just have 2 as the answer, and that is it. And so the main reason for that is whenever we take an odd nth root of a particular number, there is going to be only one answer to it. Whereas if I was to do an even nth root, let's say if I did this, then there may be maybe a situation where you will have some people say that, hey, well, this could be plus or minus 2. And technically from a number perspective, that's true. But for the definition that we're doing here today, we only take the positive answer. And so again, I'll get into that a little bit later in the video, okay? And so of course, the last one here just says if n is any positive integer, then we know that the nth root of 0 is 0. Of course, no matter how many times you multiply 0 times itself, you still end up getting 0 as an answer. So some other basic facts. So we know that for the nth root of a, where n is even and positive, a cannot be a negative number. And this goes back to the fact that we cannot take the square root, 4th root, 6th root, 8th root of a negative number. Just not possible, okay? The real numbers do not work like that. So for any real number x, it is true that the square root of x squared could also be rewritten this way, which is also absolute value of x. And so we're basically saying this here, and this sort of goes back to what we were talking about earlier as to if we have some index here that's going to be an even positive number, then we always need the non-negative answer or the principal root. And so this ensures that that happens. Now, the reason why we do absolute value of x in some of these cases here is when it says if x is any real number, okay? So sometimes we have to watch that because we don't know what x is. And so to keep true to everything, we know that whether x is going to be negative number, positive number, 0, whatever, we know that we still have to have the principal root of whatever that number x is, whether it's positive or negative, okay? So when we have an nth root where n is odd and positive, then we know that a can be negative, positive, or 0, okay? So there are no restrictions on that. And so now we get down here to the explanation of why we have to have principal roots. And so we note that -2 is a square root of 4. It is a square root, but it's not the principal root, okay? Now, the reason that if we say what is the square root of 4 like this, meaning the principal root, we cannot answer -2. The reason for that goes back to the graph of what x squared looks like. And so this is a graph of what x squared would actually look like, okay? Now, if you notice here, when we do square root of some number here, if I say square root of 1, the answer to that is 1. If I do square root of 4, the answer to that is 2. If I were including the negative answers as well, then I would have another graph that would be down here below the x-axis, okay? And so the issue with that is that if I had that, then my graph would look like this. I would have these points going here and here. This would go down. This would be at -1. And of course, this would be at -2. But now, if you notice, this particular graph I've drawn is not a function, okay? And so because of that fact, it doesn't parallel and go with everything else that I know about the real numbers. So there's a problem with that. And so hence why we want to be able to talk about just doing the principal root, okay? Because square root of x on the graph as well as square root of x, the actual number, both have to coincide. Everything has to sort of match and go together. And the way to make it match and go together is to ensure that the graph of y equals square root of x is saying the same thing as anytime we plug in a number in for x and figure out what the square root of that is, okay? So in essence, it's because of how the graph of square root of y equals square root of x looks as to why we only use the principal root, meaning the answer that is non-negative, okay? All right, so moving forward here, we know that one way to translate the nth root of a is to say, what number would you multiply itself by n number of times in order to get a result of a? And so I went over that before with this example, and I'll just do it again. Here we know that 2 is the answer because we have to multiply 2 times itself 3 times in order to get 8. So that's basically what this particular question is asking. If I said, what is the cube root of -8, then the answer to that would be -2, because -2 multiplied times itself 3 times would give you a -8. Okay. Now we know if we tried to do, let's say, square root of -4, that would not be possible because we know there is no real number that we can multiply times itself twice to get a negative number here. Okay. So this will not be possible. Now, moving on to some of the rules for radical expressions. So this first rule says that we can take an expression under a radical, which that's called the radicand. If it is a product of two other expressions, we can split it up. So for instance, if I wanted to do, let's say, square root of 8, then I know that square root of 8 is the same as square root of 4 times 2. So I could rewrite this as square root of 4 times square root of 2. Okay, so that's what the product rule says. For the quotient rule, similar, we know that if we have nth root of some fraction, we can rewrite that as nth root of the numerator divided by nth root of the denominator. So let's say if I had the fifth root of 1/8, then that would be the fifth root of 1 divided by the fifth root of 8. Okay, we could rewrite it that way. The next thing here just goes along and talks about what is the definition of a raised to the 1 in terms of this particular exponential rule here. You see how I go through the algebraic manipulation to show that. It really gets a little convoluted, so I'm not going to go through it all. But basically all this shows here is that whenever we talk about taking the nth root of a number, we can rewrite that as a raised to the n a raised to the 1 divided by n. Okay, and so we know that if n is any positive integer, okay, in other words, our index is a positive integer, then we know that we can write this provided that the nth root of a is actually a real number. Okay. All right, so from that derivation here, we can extend that fact to now talk about one of the things that we talked about in the beginning, which is anytime we have an expression, a number or expression raised to a fractional exponent, we can rewrite that in radical form. And so this is probably one of the more important things that we need to remember whenever we're trying to deal with radical expressions as well as expressions with rational exponents or fractional exponents. Okay. So moving forward here, we see that the definition of a raised to the negative m divided by n just basically allows us to be able to do the reciprocal of whatever a raised to the m divided by n is, okay? And so this comes from this exponent rule that says that you can do this. So now since you're dealing with something with an exponent, the reciprocal rule for the exponents also applies whenever we have fractional exponents as well. And that's basically what this is saying. Now, the strategy that we use to evaluate an expression like a raised to the negative m divided by n is to find the nth root, raise your result to the mth power, and then find the reciprocal, okay? And so we'll go over some examples of that as we go through this particular document here. All right, and so this last part here is just a reminder of all, well, not all, but most of the exponential rules that we need to remember here. And of course, one that I don't have here that I need to have, I mentioned it earlier, is this one, okay?